Okay, so yeah, my name is Hemel, and I want to talk about avoiding JavaScript falls through tree hugging. But before I get into that, I want to share a little observation. In the 90s and the 2000s, this seemed to be the golden age of IDEs, of integrated development environments. People were using environments like Visual Studio, Eclipse, IntelliJ, and we're actually very happy with it. And then all of a sudden, people started to switch from Java, C# and stuff, C++ to JavaScript, Ruby. And they say, hey, we don't need all this stuff. We don't need Eclipse. We don't need IDEs. We're actually very happy living in this very simple environment. And somehow, like, okay, absolutely. I see the point of using an IDE with Java because it generates a bunch of stuff for you. Like, using an IDE is like basically the only way to handle a language like C++ or Java because you need it. You need it less with JavaScript, but I still think there's a lot of use cases for good tooling for something like JavaScript. And that's my talk touches on that. So as you may know, I work for Cloud9. Who here has heard of Cloud9 IDE? Okay, so about half. So what we do is we build an IDE in the web browser. You can go and check it out at c9.io. I'm going to elaborate on it very much, but our current focus is to build a number one, the best JavaScript IDE out there, not just as a web app, but just in general. This is currently what we look like. So we have many nice features you can deploy from the IDE to, I don't know, various cloud providers. We have code completion, integrated version control, a bunch of stuff that IDEs always provided, but now we do it for JavaScript and we try to do it right. Not only are we building tools for JavaScript, but Cloud9 IDE is also entirely written in JavaScript, both on the client side and on the server side. Using Node.js. And we have currently about 400,000 lines of JavaScript code. And this is a point where you really start to notice how useful these kind of IDE features really are. Of course, JavaScript is a very nice language, but there's also bad parts. And yeah, well, we are probably all familiar with this particular book. Some people may argue that there's really not that much good stuff in JavaScript, but we are pretty happy with it. Still, there are some nasty problems, and we think we can solve it. If you consider this little code fragment, there are a number of potential problems in this code. Can anybody point some out? We have 1 minute. P is global. Yes, that's one. Yes, P is global. That's still one. Anything else? All right. So before I get into the exact problems, let me show you what happens when you load this code into Cloud9. Indeed, there's something with P. Actually, it will highlight it. It has a little yellow line underneath it. It's not very clear. It will say, hey, this P is not declared. In JavaScript, actually, that's perfectly legal. But it just declares it as a global variable, which is very likely not what you want. Second issue is the use of this inside this inner anonymous function. And this gets me every time. I don't know about you, but if you do some asynchronous stuff, especially in Node.js, and you start to shuffle code around, I make this mistake all the time. The this pointer no longer points to the person object, but points to the thing of this inner function. In Cloud9, we can actually highlight this and say, like, hey, are you sure this is what you meant? Don't you want to do like the var that is this or whatever convention you use? And then one that actually came as a suggestion from Twitter, I asked, what would make you switch from your current editor to Cloud9? And two people, actually both from Poland, interestingly, suggested, hey, I always mistype length. Can you highlight that? So, sure. So we do that now. So how do we do this? Well, we use the awesome power of static, or I would almost say ecstatic. Program analysis. So what is static program analysis about? And what can you do with it? Well, first of all, you can do this, right? What we do here is we parse your JavaScript code and we start to analyze it and report any problems we find. But you can do other stuff as well. You can do outlines, just useful IDE stuff. Outlines, code completion, like clever code completion, code navigation, refactoring. These kinds of features all require static program analysis. Static code analysis basically consists of two parts. First, you have to parse the JavaScript code, which produces something, and then you do analysis on that. So what does a parser do? Well, it reads in JavaScript code, and it produces a data structure, which we call an AST. An AST stands for Abstract Syntax Tree. So, for instance, over here we have a simple JavaScript expression a times 10, and it goes into the parser, and what it will produce is a data structure, tree-shaped data structure that says, okay, we are applying an operator here, and the operator is the times operator, and on the first operand is a variable called a, and the second operand is a number called 10. Okay, so there's a bunch of JavaScript parsers out there already. Xeon, Uglify.js, Narcissus, Language.js. These are all JavaScript parsers written in JavaScript. But they have very different, so we needed a parser, so we did some benchmarking, and it turns out that the performance characteristics of these things are completely diverse. Some use enormous amounts of money, maybe two, but memory. And some are just like an order of magnitude difference in performance. They all produce different kinds of ASTs, so different kinds of data structures, and they all have their own tools to do the analysis, which is very annoying, and it's all JavaScript specific. We're building an IDE that is currently focusing on JavaScript, but we want to do Python, Ruby, maybe Java, other things as well. So we invented, or we built TreeHugger.js. I made this slide, and then yesterday people were joking about JQuery. The point here is not to be I don't know, if you like jQuery or not, it doesn't really matter. The point is we want to make analysis of these kinds of AST accessible, easier than they used to be. I mean, you really have to be quite a hacker to build these tools until TreeHugger came around. So it does two things. First of all, it standardizes the AST data structure. So no matter if you parse JavaScript or Ruby, the data structure still is the same, and you can use the same tools to analyze them. So you get a number of standard traversals, so different orders in which you traverse this data structure, and you get pattern matching. I showed you this particular example, a times 10 produces this data structure, so we have a shorter textual notation for this AST, just to make it easier. So the AST on the left, using the A-term notation in TreeHugger can be written like this. So this is not JavaScript, this is like a little language in which you can define patterns for ASTs. So we have here a constructor that says, okay, we have an operator, which is times, and then it multiplies A and the number 10. So what can we express in this little language? Well, we have constructors, we have lists, we have strings, and we have placeholders. But I'll demo what this is all about. Funny thing is that I searched for tree hugging on Google Images, and one of the first hits, this is probably just Google being clever, this is actually one of my colleagues who took this picture during a holiday, and this came up in Google Images, so that's kind of funny. She's not aware at all of this library. Okay. So yesterday I hacked this little environment to play around with the tree hugger. So what we see here is 4 text areas. So here we can enter some JavaScript. Here you will see the AST. That is the result of the parsing. Here you can write little JavaScript analysis code, and here you see the output. So for instance, if we do this a times 10 thing, you can see on the right the AST that is produced from that. So this is updates on the fly, so you can do true. So you can see the kind of data structures that are produced. And then here we can enter some analysis code. So here we have this magic variable AST that contains the data structure, and then we can do a log to just print it out. But let me see, let's do A times 10. Okay, B plus C. Okay, so now we're interested in, like, hey, I want to know what variables are used in this program. So how do I do that? Well, I can do a collect top-down, and here match anything with a variable constructor. So you see here in this example, var A, var B, var C. So I'm interested in something that says var, and then I don't really care what's here. So that's a wildcard. If I run this, what it will return is a list of the found variables. Well, that's not very exciting. Let's have a look at something more interesting. So var I is 0. Yes, I made a mistake. This is literally what that analysis looks like in Cloud9. So what we do, we have a look. So this is the particular fragment we're interested in. So this is the property axis of the array variable with the length. So we have to match that prop axis. And then we don't care about this one, but we do care about this one. And now it produces this one. If you fix it, it's gone. And then you may wonder, okay, so how do you actually point this out in the source code? Instead of collect top-down, you can also do traverse top-down. The difference is that then you don't get any response. But what you can do is you can say, okay, I want to execute a function whenever this matches. So I can say, hello, yeah. Wrong. Right? So run, it will say wrong. This function will be executed only when this particular pattern matches. Okay, how am I doing on time? We started, yeah, so I have plenty of time. So let's do simple, let's say I want to check in my program if all my variables are declared before they are used. I'm not going to do the fancy version, but let's just do a very simplistic one, ignoring scoping and these kinds of things. So the way we do that is we can say, okay, just A, B, C. By the way, notice that it's parsing JavaScript even that's invalid, which is kind of important in an IDE because you want to get results also for invalid JavaScript code. Okay, so what we have to do, we have to keep track of all declared variables. So we use an object as a map for that. And then we're interested in two things, actually. Let me add a variable declaration. We're interested in variable instantiation, so where are the variables used, and we're interested in where they are declared. A variable declaration in the AST looks like this. Var decal init, then the name of the variable, and the expression that it's initialized with. So we can match that here. So we say var decal init, and we'll bind that to a placeholder called x. We don't really care about the initialization expression. Then we're going to use an argument to this function, which is the binding object. And this binding object is basically a map that contains a key for each of the placeholders in your expression. So in this particular case, it will have a b.x that gives you the value of what was here in this particular node. So if we will traverse this tree, what it will contain is this particular A string in the source code. Okay, so what do we have to do? Well, we want to say, okay, this is the variable that is currently declared. So whenever you encounter that particular variable, you don't have to complain. So we store that in this map. So we say declared b.x.value is true. Yeah. Then, because you can have trying to make this box a slightly bit bigger is a very slow process. Okay, so you can have multiple of these expressions here. Then if we encounter a variable, which will use x, and I'm also interested here in this thing, we check, is this x already in the declared object? Or actually, if it's not, then we start to complain. Okay. And I think that's basically all that's to it. So let's have a look. Right. So it detects immediately any undeclared variables. To actually mark this in the source code, you need position information. For that, we add node here. And node will be the value of this entire node, which has position information. So what we can do is do node.getPos. And actually do the string JSON.stringify of that. And then, okay. In addition to the variable b, we also get the start line, the start column, the end line, and the end column of that particular variable. So we can use that information to say, okay, this is where it went wrong. So this is basically the way that using TreeHugger you can build these kinds of software analyses. You'll see it updates live. Okay, so this is an open source project, MIT licensed, I think. So you can play with it. This environment is also online, so you can try different things. So what have we built with it so far? Well, first of all, the warnings that you see in Cloud9. We also have this nice refactoring feature where you can switch on like renaming of a variable, and then you can just type it and it updates the variable everywhere at the same time. We mark unused variables, so if you are declared a variable that you then don't use, then we clearly mark that. And this is something that's coming. It's intelligent code completion, so it actually analyzes the code and gives you like the real methods of this particular object. Also, all of this is implemented using TreeHugger and basically using nothing more than what I just demonstrated. That's basically what I wanted to tell you today. Yeah, so have a look at it and try it live and on Cloud9. So are there any questions?
So parsing a complete code is relatively easy task, but parsing an incomplete code or reparsing code that you add something to it, as you add, is a completely different problem, right? Are you reparsing the whole thing every time, or do you have any mechanisms to reuse some information that you already have about the code when the user changes it in the editor?
Currently we reparse, but this all happens in a web worker, right? You don't want to do this in the browser thread because it would just freeze up. But so far it's been fast enough that we can just do it on every keystroke. We delay it a little bit. You don't want to do it in every keystroke. But so we currently reparse it, but once that gets too slow for some reason, then we will consider doing like only partially reparsing, and that's indeed very tricky. So that's why I'm trying to avoid it for now.
One question? As I remember, a year ago there was possibility to download and install locally whole IDE. Is this possible now?
Yep.
Okay.
It's you can still download Cloud9. It's open source.
I got two questions for you, because a few months ago when I was first met the Cloud9 IDE, I got problem with performance on Firefox, and correct me if I'm wrong, and it works well in Chrome. So how it looks now? And the next question is, when do you I want to ask about this intelligent autocomplete. When do you want to
release?
Yes, release.
So about Firefox performance, that may be, I don't know how it is with newer versions of, in the company we are heavy Chrome users, but we also use Firefox to test, of course. I mean, we cannot really control the performance characteristics of Firefox, but they seem to work really hard on the JavaScript engine, and that's really where the performance bottleneck is usually. So I hope it's better now. I don't know when you tried it, but yeah. And when it comes to when we're releasing this intelligent code completion, I'm not sure yet, because we're currently working on some, I mean, I use it all the time, and it works quite well for me, but we have to do multi-file analysis and these kinds of things. Currently, it's only based on one file, and you want to do, like, for instance, in Node.js, when you require a file, you want to basically import the API, so you have nice code completion for all your Node.js modules as well. Probably, I wouldn't be surprised if it's still a few months away. But it's in the works.
So, because Treehugger is open source, it is possible to integrate it with another editor like Vim. Am I right?
Yeah, sure. Yeah.
More questions? Okay. Need to find some kind of teleportation here.
I have a question about speed issues. You've mentioned that your solution is much faster and better than other libraries you have mentioned. And how much faster it is comparing to, this Uglify.js or something that you mentioned on the beginning of your presentation?
Okay, probably I wasn't entirely clear there. Actually, I looked at different parsers to check their performance, and we found that at that point, actually it changed now, Uglify.js was the fastest. So we use Uglify.js. Actually, I patched it to be do error recovery and these kinds of things, but we use Uglify.js. Now, there's this other one called Esprima, which apparently is even faster. But the cool thing is that Treehugger doesn't depend on the parser per se. It just depends on the data structure, the AST. So we could easily switch from Uglify.js to Esprima, get better performance, and still use the same analyses that we already built. So you're no longer tied to the particular parser.
Waiting for another question. Okay. Could you pass?
Yeah. Do you offer auto-formatting of code?
Yes, for JavaScript, yes.
It's some predefined pattern, or I can try to define how it should be formatted?
I think currently it's predefined. I don't think you can configure it yet. But it's the right choice, so don't worry.
So, thank you.
We know what's good for you.